Good evening, everybody. Can you hear me? Good evening. Can you hear me?
Yes, Professor.
Right. Okay, thank you. Okay. Shall I share my screen again? Shall we try to discuss today about the solar energy and what are the possible one of the energy analysis also renewable energy. We know that the sun is the energy creator of the world, and all energy come to the world and what we use as even though fossil fuel, even though wind energy, hydropower, and everything is coming as a solar energy. Then the source of main energy source is the sun. We know that the main the creations, that mean the main action is a fusion reactions. Then it has a huge amount of energy. We know then it some amount of the small amount of energy may travel to the earth. It may be converted to the many uh, other form of energy sources, maybe a biomass by the photosynthesis, maybe the solar energy, maybe the wind energy, also the temperature and temperature variations due to the earth, as well as even the fossil fuel, maybe the long time ago the fossil photosynthesis convert to the biomass and it becomes the fossil fuel. The hydropower also maybe the rains coming from the temperature variations, the rains and everything. So every source of energy is due to the sun, solar energy, except maybe nuclear, because of nuclear and geothermal, maybe we can say some sort of other sources. Then the solar energy potential throughout the world, we can find out maybe the many models are developed already. We can predict what are the solar energy potential throughout the world, as well as the measurements also we can use to find what are the potentials everywhere. Generally, solar maps now there's a commonly available these solar maps. You can see here we can get some idea about how much of solar energy potentials throughout the world. Here you can see the location of Sri Lanka as well as some other countries. Then the daily total as well as the yearly total also we can present in this map in the kilowatt hour per square meter. There's one of the unit here. There's a 8 kilowatt hour per square meter is a maximum amount of some locations in the world we can find out that much of high solar energy potentials as well as very low solar energy potentials also there. Then actually today in the main area what we're going to discuss today, that how we can harness that solar energy for useful manner. Then what are the possibilities? You can see in some places like Australia as well as the Middle East, some countries, even though Sri Lanka may be not, they compare it with some of the places, actually we are receiving high amount of solar energy, but even though some places may have the large amount, they compare to Sri Lanka very high solar energy potentials. And even though the potentials is there, the huge amount of energy is there are a lot of restrictions as well as the technical barriers there we need to discuss about that, how we can overcome these things. Now, actually, the sustainable energy vision of the world, we know that the solar, namely, the name we can name as renewable energy because of this, it may not exhaust us in any way. then now there's a potential to use that. That means there are some increased potentials to using solar energy throughout these years. There's some predictions also here. You can see here. Actually, previously energy mix throughout the world. This is a world scenario. The fossil fuel is there as well as amount of nuclear energy, the hydropower also. But we can notice that after maybe 2015, the solar energy is coming to the scenario now. As we can predict that maybe 2050, the large contributions are from the solar energy. That is the optimistic view. However, there are a lot of barriers need to be overcome. Then a lot of technologies need to be developed to harness that much of solar energy. We can discuss these things in this lesson. Now, energy. When you're talking about the energy, levelized cost of energy is very much important because of the energy is always people think about how much of cost of energy generation. And that is very much important thing, even though Sri Lanka situation also. Then we should think about that, even though any environmental impact, the way their sustainability matters, the very much important thing is the cost of energy generations. Now we can see here the each source of energy generations. Here the solar energy, hydropower, even though fossil fuel, then the wind energy, bioenergy. Then the how that the levelized cost of energy is varied throughout these years from 1983 to 2021. Then the blue line is the say here the onshore wind. The wind, yes, can say that the wind, solar, and everything is decreasing. The levelized cost of energy. Actually, solar energy, the cost of energy generation is highly decreased. You can see here maybe the 10 years back, very much expensive. Now it is drastically decreased. That's the cost of energy generation by solar energy. Then we can see the concentrated solar also there, as well as the solar photovoltaic also here. Then as a wind energy also, it is very much decreased. There is a very good potential for this renewable energy one. That is renewable energy generation. The main sources are the wind and solar, because of the biomass also there, obviously. Hydro also here, but that is very much site specific compared to the solar and wind. Now, the comparatively here, you can see here, the lowest is onshore wind. Then the next one is the hydro, as well as the source, the hydro and the solar photovoltaic is there. And the bioenergy, then there's offshore wind also there. And as well as concentrated solar power also here now, it is considerably competitive. This all source of energy compared to the maybe a fossil fuel. Now, that's a very good the potentials, the very good trend. Then how that technology is improved to decrease that levelized cost of energy generation by the each technologies. Then we can discuss these things. What are the feasible source of energy generation for each and every locations. Now, this is the figure wise, it is also given there. You can see here, there's a capital cost wise also. Generally, the capital cost wise, the coal power and solar photovoltaic one. So that's kilowatt hour, the cost per kilowatt installations given here. Shall we compare with that the solar photovoltaic 1,327 US dollars when we go for the coal power, then as well as wind power. We compare these the wind power, solar, and as a reference we can think about the coal power. Then coal is much high compared to the source of energy, the wind power and solar photovoltaic. Solar photovoltaic and wind maybe somewhat closer range. Then there's some other values are there. This levelized cost of energy generation. And this levelized cost of energy generations, the PV here, if you take the 5% duty discount rate, that is for 1 megawatt hour generation for a bunch of US dollars there. Then it's a PV 110 and the coal 61. Then wind 59 around, the hydro 22. Then those are the figures we can find out this calculation. However, for exact calculation, we need to calculate the project wise. However, this roughly we have idea about what are the cost of generation, each source of energy. We can compare even the coal, wind, solar, and the hydro. The hydro may be very much cheaper sometime. This is without any environmental impact. This is only the global levelized cost of generations. Then I can see here the PV is much high compared to these these other sources, the coal and the wind. The wind maybe 59 in onshore. This offshore, obviously, that is much higher values. PV residential is much higher than the utility scale one. Then solar thermal also bit expensive. Those are the technologies. Then, however, then even the cost of energy is high. We need to think about other factors when we going for a mix of energy sources for each and every countries for maybe supply to each places. And you can see here in Sri Lanka situation, we have not the coal or oil. Then we have to think about some other source of energy because of the independence of then the foreign currency and everything. We have to think about. There are other different other factors need to be considered. However, this is a cost-wise comparison. The key factors when we going for the solar, there is system cost, installation cost, as well as there are some other things need to be considered. We need the foreign currency and what are the local contributions, as well as environmental impact. The three variables also there are the installation, how the system is financed, maybe a bank's loan and everything also need to be considered because of those are the project developments. Then need to be these things very much effective factors when we going for a solar power generation. Then the cost of energy generation we already compare with some other source of energy. It is highly decreasing trend. Then in the photovoltaic, due to the modern technology, the people develop many technologies from the silicon to the thin film technology wise. You can see here. Then it is decreasing up to after many years from 1980. You can see a very high amount from what's the present value there. Then even though we can think about what are the future trends, then if we're going to develop some policies, then we have to check what are the future trends of the cost of generation by the solar. Then those are the curve here. This global market also we can predict it. So what are the historical values also improving trends also they are from 2018 up to 2020. There's a predicted values of 2027. Then what are the megawatt hour scale? Then the medium scenario also here now in the present situation 229 is a megawatt. There is a global market size. Now you can see here is a future trends also there. Then if you're going for any solar project development or the project the developments in the technology developments also, These are good trends. They are the people are always the increasing trends of the global market. There's a rooftop solar that is 2023 is 159 gigawatt hour. That's the present figures. Now, shall we talk about a little bit about some terminology, what we're going to use in this lessons? Those are some terminologies here, the irradiance and irradiations. Then terms of the irradiance is a watt per square meter. That means energy. What mean how much of energy we obtain per second? There's a watt is there. Then watt per square meter, we are calling this irradiance values. The symbol of that value is G. Irradiation means energy content, how much of energy per any given period. Usually that is per hour or per day. Then generally it's joules or kilowatt hours or joules per square meter per day. Then we are calling this irradiance values. Then other two terms there is a insolations term also, using how much of energy received by the solar. The radio city also some other term, the rate of radiance energy given from surface per given area. You have to keep in remember these terminologies. We are going to use any our lessons or any calculations or any definitions. Those are the main terminologies we can use here. Some concept, some theories behind how that energy is coming from sun. This one concept is that we are calling Stefan Boltzmann law. Energy. This energy emits from any high temperature body. We can define by Stefan Boltzmann law. The energy is equal to this energy is proportional to the temperature power of 4. That is the Boltzmann constant. The sigma is the Boltzmann constant. Here is where that is 5.67 10 to the power of minus 8 is given there. Then any the high temperature. See, if you know the temperature of any given body, then we can find out how much of electromagnetic radiations emit by that body given by that. The sun has some the temperatures there because of the in between sun is a radiate energy. The main source of energy coming from the medium of the sources from the sun to earth is radiation, because of there are no any conduction, no convections can be happening because of no any material in between there. Then only transport concept is the radiation. Then the temperature of the sun is there. Then we can find out how much of energy radiate, how much of radiation emit from the sun. Then the temperature is the main important factor. Then this is the equation we can find out how much of energy can happen there. As well as we know this radiations has some frequency. The frequency, low frequency and high frequency energy is coming from there. Then the temperature again is coming here. The C is a constant here. The T is the temperature. The C is a constant there. Then there's lambda is the wavelength there. That's the reasons here. Sun radiate with high frequency values. It's come to the earth. There, so earth also have some temperature. It also emit back some amount of energy because of that our previous law. However, the frequency is we receive very high frequency, but the return back is very low frequency because of the low temperature in the Earth's surface. Then the sun temperature is 5,800 Kelvin. This Earth temperature is 280 Kelvin. then you can see here, that's the reason the greenhouse effect is happening here because of the low temperature. It emits a low frequency. That means high, the long waves. The long waves can be trapped by our atmosphere. Then that's the reason we remain some energy throughout our that's actually warmer. That's the reason our the temperature is remain. This is a global warming, but we are always a global warming because of some gases like carbon dioxide, some gases may be a very high effect of the return of the long wave things. And if we have that composition, high composition of the global warming gases, that we are called the greenhouse gases, uh, the Earth temperature going up because of our returning about. That means the energy emission from the Earth maybe to prevent from that type of gases. And there's a Wien's law. The Wien's law, we can explain the temperature and the wavelength of the body. And there is one thing. Other important parameter is the inverse square law is important because I is the intensity of radiation. The D is the length. The D is the length. Now we know the sun has some intensity. There's a D is the distance from sun. Then you can see here, if it's a high distance, then the intensity of radiation is low. That as the intensity of radiation is directly proportional to 1 upon D squared. Then we can use that to find out the solar constant. My next slide, I can explain that how the solar constant and the length between the distance between sun and the Earth correlations. Actually, the Sun-Earth relationship is very much important to understand it. Now, solar constant. The solar constant is the value where that intensity at uppermost atmosphere. Then actually we are calling this is the solar constant value. That's the solar constant value that is in the uppermost atmosphere. Then actually what is happening now is this solar constant also not equal throughout the year because we know the sun, the Earth is rotate around the sun. See, there's a elliptical orbit. Then distance from the sun to Earth is not constant throughout the year. It is varied. Some month it is very much closer, some month it is much higher due to that elliptical orbit. Then we know our previous equation. Then d squared is there. Now d is varying here. The d is varying here. Then I also not constant. Now the solar constant throughout the year is not the same value, but we can assume that some average value is there. However, if we want to find out the exact value of the I, we need to find out the location of the Earth in a year. Then we can find out what's the solar constant and each and every month. Actually, there's one equation here. This is the value. This is the value we can find out as a solar constant. However, then if you need to find out the exact value for each and every month, that means the number of the day, which day we are passing through our orbits of the sun, then we can find out the exact radiation. That means how much of radiation we receive to the Earth, we can find out like that. This Earth is there. It's the uppermost atmosphere. If we find out any spare meter here, it's the energy received from the sun is this way. Actually, we are calling this a solar constant. Then actually energy transfer from here to there, some other effects are there. We can discuss these things because of this uppermost atmosphere. That's the value. If we need to find out these the value of this radius, there's an R mean what's the value, what is the distance between actual distance between Earth and the Sun, we can calculate by this equation. Actually, this is the equation, is a polynomial equation we can find out here. There's an orbit, there's a path is defined by this elliptical orbit. By using this equation, we can find out what should be the R there. Now we know how much of energy is coming to the uppermost atmosphere. Then this type of solar map, the solar map actually is exactly we can model how much of energy we receive from the from each and every locations by sun. However, it's not the same. There are some variations are there. That is maybe due to atmospheric effect. There are a lot of atmospheric effect. Actually, large amount of energy can be absorbed by this air in between uppermost atmosphere and Earth as well. There are some sort of reflections also there. Then those are the effects we can find out. Then if we need to model these things, actually we can measure these. Then how there are a lot of models we can find out, because if we know what are the substance in between this area, maybe a cloud cover, maybe a moisture, maybe a particles, maybe a dust particles, maybe some other particles. If we know those things, we can find out exact amount of energy received the surface of the Earth. Because of the uppermost atmosphere, we can model by our previous equation exactly. That is solar constant and location of the Earth in each and every month. Then actually the solar resources thing is much more convenient to predict compared to the other resources, the sun and the wind resources, because of it is very much direct, very much straightforward. Because if we know the substance between our atmosphere, we can predict how much of energy received from the sun. Then actually cloud cover and everything also can be predicted up to some level. Then this is a very good explanation. The solar constant is there, uppermost atmosphere. Then it absorbed by some amount of absorbed by ocean, ozone. This percentage also we can find out. Other thing is that there are large amount of air molecules also there. There is a scattering effect and absorption. There's 15%. Then there are some aerosols also there in this atmosphere that also can be estimated, as well as the cloud also which reflects, scattered as well as absorbed. Then actually sometimes it's maximum 100% can be covered. We know that. And water vapor also absorbs some amount. Then the ground, then it is come to the ground. Then even though here that is 1,367, maybe here, maybe it is 1,000 sometime. That is these all are the remaining things the loss by in between there. However, it's 1,000, sometimes 1,000, maybe less than 1,000 sometime. That depends. Actually, we learned this correlation before. I'm not going to explain it again. What are the correlation between these things? Global horizontal radiations, as well as atmospheric moment also. There is some moment of diffusion due to the air and cloud and everything. We know that how much of diffuse horizontal. Actually, we know that after the sunset also there are some light here as well as the shadow also in any high shadow many buildings or obstacles. There's some light also there. We are calling the diffusion like this there. There's some energy. Then actually shall we little bit talk about that Earth Sun relationship to understand how that the solar angles and everything is happening. We know Earth is tilted presently 23.5 presently. Then that is tilted. Then it rotates in that elliptical way. Okay. Then there's a north. There's the northern hemisphere, the southern hemisphere. Then if it is this type of location, we know it's a north, that's the northern hemisphere is much closer to the sun. Then if it is this location, it is southern hemisphere is much closer to the sun. Then you can see the sun, this radiation is coming, the sunbeams is coming there. Then you can see how much of the solar energy received the square meter is depend on these inclinations. We can discuss these things. The effect of the northern hemisphere as well as the southern hemisphere is that the seasonal variation we can observe due to that that inclination angle. This inclination angle is very much important. This all the seasonal variations and rainfall and everything. This everything is happening due to 23.5 degrees angle. All the ocean currents and everything, monsoon and everything is happening due to that reason. If it is a zero angle, maybe that human mankind maybe I don't know that the water cycle and everything is not work properly. That's very much important. That is 23.5. Then there is a, if we see from the north side, there's a north pole. There's a north pole. The 1 year, the meaning of the 1 year actually, that inclination is very important. That's orientation of this Earth. Shall we think now? This is the orientation of this Earth. So after one year, it's the same orientation. What is the same orientation? It's the same orientation. After one cycle, it's come to at the position of the same orientation. We are calling it 1 year. It's a 1 year. It's a 1 year is not equal to the one cycle of rotation because of this. This is this axis because of the 23.5 axis also oscillations some amount. Very small oscillations are there. Then however, the 1 year we can observe this physical 1 year we can observe that this our orientation of Earth after some period, same orientation we are calling that is 1 year. We maybe that may not equal the exact one cycle. That's been the reason that our some the location of the stars maybe varies with the time. The location of some the distance stars is not very sometimes. That's the reason exactly. Sinhala and New Year period also vary time to time. If you notice that maybe 20 years back, can you check your calendar? Maybe it is April 12 and 13. Maybe it's now maybe the 13 and 14. Then that is the reason of that because of the 1 year. There's a 1 year maybe not exactly equal to the one rotation of Earth there. Then how that also very important factor when we find out the Earth, the Sun rotations. I'll listen a little bit about that because of the solar tracking and everything. if you want to find out this angle of things, we have to consider very small variation also here. However, then there is some other the same explanation here. Then we are calling this a declination angle. There is a declination angle. Then same orientation here. There's the same orientation. So March 22nd, and this is the value of the December 20 and March 22, June 22, and September 22. Those are the four important positions. Those are the four important positions, the peak point. The December 22nd also one peak point of that location, and so the June 22nd also some other peak point. Then, because of here, this is September and March, then this axis is this inclination is the same plane of the sun there. Then in September and March, then the solar radiation comes directly throughout the world without any effect of that inclination angle, because of that inclination angle is the perpendicular, that is perpendicular to the sun. This is sun is there. That's the reason in this point the north and north pole, the north hemisphere as well as the southern hemisphere, we see same amount of solar radiation in these 2 points, September 22nd and March 22nd. Then the December and June maybe here, the vice versa. It's there is totally different. Now, so declination angle is the important point. The declination angle is depend on this variation, this variation. Then here, this declination angle is here is 0. In this point, this is 0. That is declination angle is a maximum point, that is 23 point. That is relative. This declination angle variation. The declination angle variation throughout the year we can explain by this graph. And these 2 points are exactly 0. Then this is the maximum point. These are the other maximum points. Then the solar radiation received, this declination angle is that there is important factor. And we can find out that. Declination angle also we can calculate it by this equation is there. This some equations it's derived from this orbit of that Earth orbit around the sun. Now, why the declination angle is important? You can see here the radiations. The energy content of this amount shall be equal, same. Shall means energy is same. Energy is same. Then if it is come to this point, then the surface area. The surface area is much smaller compared to this surface area. This energy A1 and A2. A2 is higher than A1. Same energy. Then if we find out how much of kilowatt hour per square meter, then this A2 is the surface area. Energy shall be here. This energy divided by A1. Here, energy divided by A2. Now you can see here, this is high amount because of A1 is much less than here. This one is much higher than this one. This is the energy intensity. This energy intensity of this inclination angle as well as the location of the, you can see here, it is depend on that the inclination angle as well as the location of the Earth. Even the polar region, it receives low intensity of energy compared to the equator, as well as it is depend on the inclination angle also. If you think about the June, this month, May and September, then this only effect is the polar, and that means the polar and the regions, equator and polar. Then is other months, the both effects are there. Then because of the inclination, that's inclination angle also much more affected. You can see now the December 27th, like that. That is the December 21. The Earth is this Earth orientation is like that. The sunbeams is coming there. In the southern hemisphere, energy intensity is much low compared to the another hemisphere. Then this azimuth angle also another factor. Which we are calling the azimuth angle. Sun is here. Then it is observer is there. Here, this is the angle from vertical to angle of the sun. From vertical to angle of sun. Then fortunately, Sri Lanka, we have some period, we have that almost our sun is ahead of Sri Lanka. Then we have that zenith angle and azimuth angle. Then is actually this is the azimuth angle mean north and south. This is the angle we are calling zenith angle. We are calling this zenith angle. This is the vertical location here. Then here is the horizontal location. This angle we are calling location of the sun. We can define by these two angles. Now, some places, the sun is moving like that. The sun is moving like that. It is behind the projection of our Earth there. Sun is moving. The sun is maybe a sunrise from here, sunset from there. Actually, sunrise not only from the east. That's depend on the location of the Earth. The country like Sri Lanka, we are not much affected like this type of effect there, but in the country in the northern and the southern hemisphere, sunrise not in the east always. That may be some other locations. Sometimes it may be like this location, it may be projection like that, like this type of projections may be there. This is sunrise. This is even a sunset. Sunrise, sunset. This is the projection of sun path. Then the real sun also we can observe there. Then actually these two angles we can find alpha and this alpha is the zenith angle. The zenith angle is coming there. The location of the sun we can find out this angle from the south to there. The south to there. Actually, the south is because of this angle we are calling zenith angle and zenith angle. Now, other thing is that the number of days. This is so I have to explain that the day, number of days, how we can explain the number of days. Is not there's a rotation. The one rotation of the Earth here. Shall we think this type of place? Now Earth is moving around the sun. There is some motion is there. Shall we think Earth is located in this location today? It may be after 24 hours, it will move to some amount. Then the sun angle is there. Then the Earth is moved to this point. Then this angle is like this type of angle is there. I'll draw like a little bit clear diagram. Shall we think this Earth here? Now, this is the angle. The one rays coming here. So one day it will move. Shall we think one day it will move like this one. Now, this is the location. The first, it should be come to this point. Shall we think it's sunrise? Shall we think 6 a.m. morning there? Then after one day, this also next day 6 a.m. Shall we think like that? Noon, no? Shall we think noon? Here, the first day there's a 12 noon there. It's 12 noon there. Second day, that's a 12 noon here. Now, it is more than one rotation. You can see here. Now, it is more than one. It is more than one rotation. It is exactly one rotation. It should be the same angle there. It should be same. That's the same angle here. It will the Earth may be rotate a little bit more, more than one rotation for one day. Actually, exactly one day mean it is not exactly one rotation of the Earth. It is not exactly one rotation of the Earth. It is the same position of the sun. After the one rotation, we can observe the same point of the sun. We are calling there is one day. Actually, we are calling this one day. That means the 12. In this position is a 12 noon. This position also 12 noon. There's a one day. Now it is come to this position is little bit it's a more angle need to be rotated to the same angle with the sun, the same angle with sun, because we observe, because of our days we are defined with respect to the sun. Our days not define the one rotation of the Earth. The other important point is there. Now, this is the elliptical path. There is the elliptical path. Now, this distance, this is the one distance we have to mention. This distance is d1. This distance is d1. Now, if this distance is d1, the speed of the Earth also not same. Then it's taken this angle. This angle per one day is not same each and every day of the Earth. Maybe in the closer to the sun, like in the September 22nd, that the Earth speed is much more high compared to these locations. These locations. Then actually, if we define solar day, if we define the solar day meaning from this noon to next day noon. Exactly this day noon to next day noon, we are calling solar day. Now, if the daylight in September 27, the Earth motion, Earth speed is little bit high, then it take in the one day, it maybe in the one day, Earth can be go faster. That means the Earth can be a little bit go faster compared to December month. That means D2. That means D2 is maybe higher than D1. That distance for one day. Then this angle also not same. Now you can see here, the solar day also not same. The solar day is not same throughout the year. That's different with the location to location. That's the different location of the Earth orbit around the Earth. But our standard time per day is equal, because we are not going to change our 24-hour time per day. That is equal because of that our clock is working independent of the sun. Then our clock day is defined. Then the average day divided by the 365.25, like that type of equation we are using to define one day. One day is a clock day. It is not exact with the solar day. Now, if we go for a solar energy, there's a solar day is important. The solar day is important. Now, this difference can be calculated by these equations. Actually, we are calling the solar time and standard time. The The solar time is depend on what I already explained previously. There's a solar day that means noon to noon. There's a noon to noon time. It's noon to noon time. Then our that the standard time being our clock day, our clock time. Then that not change with that mean the day in September. Day in September is not it's the same as day in day, day in December. Then now actually we can find out this correlation between the solar time and standard time as well as some error also there because of exact the longitudinal point because the standard meridian also there. Then we can use these equations. Now this may be important sometime to find out about the Earth, solar, the correlations within the solar time and solar sunshine hours and everything is depend on these things. Actually, now this is the variation. This is a variation of that our solar day and standard time. You can see some 15 minutes, 20 minutes variations are there throughout the year. Actually, this variation due to the speed of the Earth, the variation of the speed of the Earth rotation around the sun. We know maybe the sun, if it is the distance is high, the location at the distance is high, the sun rotation speed is less compared to the low distance. Now, this is the we are calling some our angle also we can define. So our angle also we can define that is defined by the sun location. The sun location, our angle, then actually we can define by this equation generally. The 15 minutes is there. Then it's 12 noon. We can find out that is standard time. Then how much of angles coming there because of from noon. So noon we are calling the zero. Then after the noon, the how much of the variations. Actually, that our angle we can define by omega. Then if it's a sun sunbeam is come like the sun rays is come like in these locations. Then if it is what is in that that is in our observer meridians, then it is the standard we are called this is the our locations. Then this is the meridians, then the sunbeams are coming there. This is the angle we are calling our angle. This our angle also explained by this explanation very clearly. This is called we are calling that there is a our angle. Those are the meridians. Then we are calling this solar moon meridians. Then after how much of the change there, then we are calling this this is the angle it changed with here. Actually, if you go for a sundial, the sundial is using this concept. The sundial is using this concept. Now, these equations can be used to find out the real time and the angle, the time can be calculated. As homework, if somebody is interested to follow these things, you can calculate it. That's how you can convert that sundial time to real time. Because there are some variations. There's some small variations are there. That variations due to that that variations are due to solar day and the real day. This variation, the solar day and real day. This is some small variations are there. The solar day is depend on noon to noon with respect to the sun. The real day is there's a clock time because the real day may be 24 hours. The sun day, the solar day may be not a 24 hours. That vary throughout the year. That is depend on the location of the Earth. Now, this seventh angle also we can find out each and every year. to the world. Now, the annual global radiance can be calculated. That's the point here. Because of the annual global global irradiance can be calculated by this equation by using this Earth-Sun relationship. If we know these angles and everything, we can find out what should be the global irradiance. If the for the four clear sky conditions, then actually we need to add that the sky those atmospheric conditions to find out real situation. Then these are the model we can use find out this is the way how we can find the solar energy calculations by throughout the Earth and each and every day. Now the day also there, then each and every day how we can find out how much of energy received from the sun. Then there are some other models to estimate the cloud cover and the atmospheric conditions. Then some positions also very much important. The some positions. Actually, some positions. Why would we want some positions? In a solar energy concept of solar energy, can some student can answer that why we require the some positions for energy harnessing to calculate some position.
To maintain the better area of the solar panels.
Solar panels. Maybe you may aware about that solar trackers, no? Solar tracking. Some panels people are using the tracking concept. The sun can be tracked by solar panels because of it can be harnessed high amount of energy. If we can track the sun rather than fixed mounted solar, then maybe one good opportunity because sun position is important. Then how we can find out some position? Yes. Then there are different technologies are using here. Then I'll explain a little bit later on why these the technologies are. Did you hear about that the solar panels and maybe a parabolic, especially for a parabolic solar collectors, it is required to use sun position. Otherwise, it cannot be focused into the correct the focal point to the there. Yes. Now, actually, these all angles, what I explained, that you can follow these things, how we can find out some position, this zenith angle and the location of the sun in the Earth, sun relationship is very much important. Otherwise, we cannot find out this type of geometrical equations. Actually, this is coming from very much fundamentals. Then this is a 3D geometry. Then these angles coming there. However, this is a little bit difficult technology to track the sun. Then if the parabolic solar collectors need to be change the position throughout the day, throughout the year, then need to find out. But in some modern concept, people are using some other concept, maybe the hill climb method, that is a maximum power point trackers also people are using now because of this type of difficult tracking concept. Okay, however, we need that some positions. Actually, these are the algorithm people are using. If you can find out, these are the algorithm people are using for these solar trackers. Because of solar, otherwise, maybe the solar panels, the most of the time we are using fixed angle, that means fixed type solar panels. But some places we can use actually the tracking concept of the solar panels. Then there are some algorithms are there. If you need, you can use this reference, then find out what are the radiation algorithms. Now, it's a mounting angle. It's a mounting angle of fixed collectors. I'm going to I'm come to this point very quickly. Now, the sun is there. The sun is there. Then the alpha angle, does the alpha angle mean this is the alpha angle? That be perpendicular to the solar panel with angle to the horizontal plane. We are calling the alpha angle. That can be that is exactly equal altitude angle. We can say that because of we can do that angle. Then this delta is a declination angle. The declination angle, can you remember? We already have the declination angle there. This is the declination angle. The declination angle is varying throughout the year. This is varying throughout the year. Then, if that now this declination angle is varying throughout the year, it is varying throughout the year. That is varying throughout the year as a sine wave. As a sine wave. Now, there's yearly variation. If we neglect the daily variation, yes, you just know that the sun is varied, sun location is varied throughout that is throughout the day. Day also some variations are there. Then if the fixed collector, then actually if we cannot track daily variation of the sun, then if we can think about that the variation of yearly variation. The yearly variation we can find out by declination angle. That is a declination angle. Then it's a 12 noon. Shall we get at a 12 noon? At a 12 noon. At 12 noon. This location. At the 12 noon. If it is perpendicular here, this should be the best angle. This is the best angle. It is phi. The phi angle is the latitude angle. Delta angle is a declination angle. That means the declination angle is varied throughout the year. Now, shall we think like this type of locations? Now, if you go to fix solar panel, what do you think about that? Shall we go with this example? Then what should be the best angle solar panel installation in Hambantota? If some student can give answer for my question, what should be the best angle for solar panel installation at in Hambantota?
Six degrees.
Please, little bit loudly.
Can it be 6 degrees, Professor?
60.
6.
Why? What's the reason?
Because it's pretty much similar to the latitude of the location.
That is the location. Then why you are neglect that inclination angle? The declination angle. What's the reason you are neglect this angle? What is the reason? Yes, that is now declination angle you are neglecting. What's the reason? Now the best angle, you can see here the best angle for
Sri Lanka is almost on the equator.
Yes, but the declination angle is varying. Even though equator there, the declination angle is dependent on the 23.45 inclination of the declination is depend on that inclination of the. The reason is that you can see here the mean value of declination angle throughout the actually we are not going to change our solar panel, no? The mean value of the declination angle. What's the mean value of the declination angle throughout the year? It is 0. it is 0. That's the reason. Then if we take if you are not going to change our solar panel with the time of the month, that means with the period of the month, we can neglect. We can neglect the effect of that declination angle, because of the declination angle effect is, yes, there are some effect is there, obviously, but if it is, we can assume that we can neglect that. The reason is that is the 0. Then that's a very, very important point here. Then the summation, we can assume that there is 0. That's the effect of declination angle throughout the year. It is 0 because of it is minus, plus, and everything is there. That's the reason. If you go for Hambantota, yes, your answer is correct actually. Then the angle should be this value, exactly this value. That is in Hambantota, there is exactly should be this value. And if you're going to fix any fixed solar panel, the fixed one, what's the orientation of the orientation of solar panel? Face. Where should be to face? This orientation. This angle is 6.1 something. Here is correct. What should be the orientation? Direction. Orientation means like that thing. This is east. This is south. This is west. This is north. Which direction it should be faced for a solar panel?
East west.
Huh?
East west.
Why is west?
The high power can be generated. That the waste is less.
That should be south.
Due south?
Then somebody can explain that it should be south to north, because the west and east should be sun is coming from east to west generally. Then actually face should be south to north, no? The angle actually like that. When we're going to fix the solar panel, this is the angle latitude. What should be this direction? This is the point that I asked. This is north or south? That's north or south?
It has to be due south.
Yes. Why? What is the reason?
Because Sri Lanka, like Hambantota is just above the equator. So basically in the northern hemisphere.
Yeah, that is the reason northern hemisphere, not near the equator. That equator point is coming there. There is an angle coming from here. And if you are going to install any solar panel in the northern hemisphere, panel should be oriented to the south. If the panel should be installed in the southern hemisphere, the panel should be oriented to the north. Is it okay, or is it clear? Because of in Sri Lanka, did you notice that the most of the time period the sun is moving in the southern hemisphere, because we are in the north there. We are in the north there in the most of the time. Then naturally in the Sri Lankan situation, we are not much clearly observe that situation. If we are in the country like Western country, the country like near to the North Pole, the sun is always in the south. Sun is always in the south, because of you cannot observe your sun in the north there, because of you are in the northern hemisphere. Then that's the reason. Like that, if you think the country located, shall we think in the country located maybe Sweden, maybe that latitude is around 40, 43, like that type of places. Then our solar panel should be, the angle is 43, is faced to the south. Is it clear? Then because of this exactly south. The thing is that the rooftop solar is the question here now because of the roof that roof structure may be very much affected to your panel fixing. That maybe you have to think about that for a more high efficiency. Your solar panel orientation and these angles need to be comply with that angle as well as the orientation. Okay. Now, these things I will little bit explain a little bit however. Then shall we do quickly now? Actually, we know that this solar constant is there. This is solar constant. The variation throughout this our country due to that other effect. Those are the other effect. Otherwise, because Sri Lanka is very much small country-wise, geographically maybe not much distance because we are located around the 6 Hambantota, 7 or 8 in Jaffna. In between that, the total country is there. Then even though there are small variations due to other reasons, maybe a moisture, the moisture content of the atmosphere is not same throughout the country. The high moisture containing the wet zone and the cloud cover also not same. This is the reason that the global horizontal radiations in the middle of the country little bit there are some variations are there. Actually, the height also very much important. Can remember in our previous equations. The height also very much important. Height at the higher elevations, higher amount of energy is coming there. Then if the less amount of cloud cover in Sri Lanka, also the high elevations, high amount of energy can be reduced. Then maybe the temperature also less. Then our solar panel will also work in very high effectively at low temperature. Then that's depend because of that the cloud cover may be other reasons. Then direct normal radiation to Sri Lanka throughout the months, each and every month also we can find out. Actually, all the solar maps are developed by modelers. These models are validated by the real data. This is the way the solar maps develop because of that we know that now also we have the very good idea about that how the maps and the solar radiations can be calculated. Now also you also can calculate it that each and every day of the year. Then we have this data. In the clear sky you can calculate how much of radiance coming from sun. By using the location of the Earth, by using the Earth-Sun relationship. Then need to be at the other effect, atmospheric effect. Because of the solar maps in Sri Lanka, we can use this solar map if you are going to install this type of solar panels, then you can calculate it, how much of energy are there. Now, can we talk about what are the applications? Actually, the PV is not only the concept of conversion of energy from solar to useful energy source. So we know the useful energy source mean electrical energy may be one of the useful energy source. It has high exergy value. Yes, we know. Because of that, if we convert to the electricity, we can reconvert to any source of energy. Then if we have some other energy source, maybe a thermal source, maybe a mechanical energy, we can use some other conversion technologies by solar. There are some technologies there. Solar thermal electric power conversions also people are using. Actually, we can use steam engine or turbine by solar energy. Stirling engine is now very much popular. maybe in some satellites people are using for solar because of the conversion. Conversion efficiency is very much high compared to the photovoltaic because of it works the Carnot cycle efficiency. The Carnot cycle efficiency we can maybe up to reach, we can do 60% like that type of current conversion efficiency. Then yes, cost of energy maybe the other bit area. Then we can think about these things. Solar updraft towers and concentrated solar and everything are everything's are there. Other very simple technologies also here. The solar collectors also people are using. We can use the hot water by thermal hot water collectors as well as the drying purpose also people are using. We can use as there. Solar photovoltaic, yes, there is direct conversions. Those are the main type of technologies for application of solar power. We can discuss these things little bit, not much deeply because of we hope to discuss this in the semester 3. However, as in the introduction, we can discuss up to some extent. Now, hot water heating for buildings, it's for photovoltaic thing. Solar refrigerations also there. Solar refrigerations, yes, in Sri Lanka, yes, yes, some places I noticed, maybe some hotels, people they are using solar refrigerations and air conditions. Transportations, yes, so solar energy can be used. We can discuss how we can use transportations by solar energy. Desalinations, yes, people are using. The photosynthesis plants also there. That is the natural phenomena. Then other all those things are different technologies we can use for each and every applications. The photovoltaic and heat engines for electricity generations. Hot water building heating and cooking is seldomly used, but the building heating is most commonly used. Yes. Solar collector types, the flat plate collector, and there's an evacuated tube collectors as well as the concentration collectors. We can use for this thermal applications. The flat collectors, the concept is here. There's a greenhouse effect we are using there. There's a glass plate piece top of that collector. Maybe a double glazed collector are there. Then the solar radiation is come inside to that collector because of I already explained that the solar radiation has a high frequency because of the sun has high temperature. In the Wien's law, it's we can explain that what are the frequency of that solar radiations. Then it reached to that solar collectors. That the temperature of that solar collector is somewhat low. It can radiate again low frequency, high wavelength radiations. It can trap inside that solar collector because of glass has some effect there. It cannot be trapped that low frequency radiations. It retain some amount of energy. There's a basic concept of the flat plate collectors. Actually, we are calling that is almost similar to greenhouse effect. Now that efficiency wise, that evacuated type collectors little bit high compared to the flat plate one. This tubular one, the shape of that architecture as a tubes, it can harm. It can collect a much more higher amount of energy compared to the flat plate collectors. Now, so energy also another important one. Then you can see here the conversion efficiency and cost of energy. is little bit different concept here. Then conversion efficiency mean per square meter how much of energy can be converted to the useful energy source, thermal energy source. Then if we think about the FK tube, it's much expensive. Even though if we are using less surface area, you have to think about that. Then for a solar, most of solar and wind type of renewable energy sources, energy is there. Actually, energy is free. That is there always. If we have no any restriction about surface area, then we have to find out what should be the good options there. And he said, this is the flat plate collector one. Type collectors. Conversion efficiency and cost of energy need to be considered for each and every technologies. Concentration solar also very common concept. Parabolic collectors are there, the solar. In this point is very much important that the tracking concept, otherwise it cannot be focused into concentrating point where that high temperature point. Then that focal point is here. The large amount of solar radiation can be reflect to that point. At that point, very high temperature can be used for thermal energy, converted to the water can be converted to the steam. That steam can be used for a turbine or some other applications for convert to mechanical energy. Just the way is convert to solar energy to mechanical energy. Then so sometimes we can use the very efficient solar panel and convert it to the electricity because of high amount of energy is there. There's concentrate in solar because of that solar collector material may be less expensive compared to the solar PV. Like this type of concept, maybe a thermal conversion can be used. Those are the one concept here. Then other solar electricity is very much useful. We know if we convert to electricity, it is exergy of that source of energy is very high. Then we would like always convert to electricity. Then it is very much convenient for us. That's the reason photovoltaic energy is very much popular throughout the world. It's simple because of no any moving parts there. Then it's direct conversion solar rays to electricity. Then even though sometimes the low conversion efficiency, people maybe would like to use that. Now, obviously now the modern technologies say now that conversion efficiency is improving and improving. Then I already explained that the solar thermal energy generation. Think that it's the low cost sometime. However, that's depend because of complex collectors and so solar tracking concept should be there. Then if you go to the solar tracking concept in all that the geometrical and all those things, how we can track the solar, otherwise it cannot be focused into the real location of that the steam generation for that point. Then there's a parabolic one as well as circular shapes, solar collectors, people like using. Other thing is that if you use that type of collectors, we can use steam engines. Then the conversion efficiency is a little bit high because of that Carnot cycle conversion efficiency is there. Then that is the practical limit is around 60 to 35. This more than 35% conversion efficiency is there. Then naturally in the photovoltaic maybe cannot be come to up to that level. Then as conversion efficiency is there. Then again I explain again and again we have to think about cost of energy always. The cost of energy is the important point rather than conversion efficiency. That is a very good point here. Shall we think like that? If we have the low conversion efficiency solar panel with low cost, then if we have no any restriction of the surface area, then we have to think about that, which type of solar panels we need to use to conversion of the same amount of energy can be generated by high amount of surface area. Then if there are no any restriction of surface area, we can go for that option. Then that's the reason. Even though that the current cycle efficiency is very much high, the cost of energy of the solar thermal generation is high, then we have to think like that. Those are the concept of energy. The photovoltaic conversions, I will explain a little bit. There are many technologies there. Actually, solar, the sunlight is coming here. It's directly converted to the electricity. We are calling the photoelectric effect. This photoelectric effect is using there. There are many technologies there. Then actually present days the third generation one, high conversion efficiency, as well as cost of energy also much less. Now, this is also very controversial factor. People think about that energy payback period. Even that energy payback period, the meaning of that energy payback period, we know that we require some amount of energy at the point of the production of solar PV or some other product. Then actually the silicon process, it required a high amount of energy because of that high temperature process is there. Then the conversion, the material conversions may be high amount of energy, very much energy intensive process for a solar panel at that time. Now the same the which amount of energy it required for the production stage, that the same energy can be generated by that solar panel, we are calling that the energy payback period. We are going to say energy payback period. It's a money terms, that is not in the money terms, the energy term. We are going to say energy term. Now with the different technologies are there. You can see here that the mono silica is around, we are calling this 2 years like that. Actually, that's depend on technology, concept of technology. There's now this is very the modern technologies. Time before the five years back time, the technology people are using, the energy payback period is more than sometimes 10 years, sometime for a solar panels. Now it is very compared to value of the 2 years time. That means that it required 2 years time to generate which amount of energy it consumed at production stage. Yes, yeah. Here is the lowest. That type of solar panels is the lowest energy payback period. Then is a life cycle assessment. If you go for a life cycle assessment, we can very clearly define these things about the feasibility of the technologies. Then actually, say energy payback period of some locations is a energy payback period. This is the energy payback period. Each and every location wise, then some locations you can see here, even though like this type of things, we have to think like that because of technology was 8.9 years energy payback period. Then just depend some locations and some technologies. However, compared to the other source of renewable energy, that may be solar, the wind, and other source of renewable energy, energy payback period of solar may be compared to little bit high, very high. Then this life cycle assessment need to be for in detail and we have to consider life cycle assessment, the feasibility of each source of energy generations. I'm not going to talk too much about the concept of that the PV concept. Actually, the photovoltaic effect is coming there. Actually, in the manufacturing stage, the cells are there. The cells we can develop up to the modules. Then the modules, then we can up to the array like that. The cells, modules, arrays. The cells is the single cells. Then it can be the single modules. Then the array. Actually, people are using the array. Those are the array. Now, this performance of this solar PV is need to be understand. Then how it's performed. Then, shall we go for that one? That one. There's a power curve of the solar. The power curve solar. Then there are few tests we can do how to find out solar PV performance. We are calling the short circuit performance as well as the open circuit performance. Then actually the short circuit means the voltage is zero. It is the open circuit means the current is zero. The current is zero. Then if you go for this type of concept, the measurements, we are calling the power curve. Power curve. Then for a constant irradiance, we can change that the current drawing through that solar panel, the panel curve like that. You can see here. Actually, the short circuit one, the point of short circuit, then voltage is zero. The voltage is zero. There's some measurements, high current. It's an open circuit. The voltage is 23.6. There's no current there. Actually, the power is the power meaning is that voltage and current. The meaning of the power is voltage and current. The power is voltage and current. That's voltage and current. Now you can see the power. The power curve we can do by this yellow line. Now the power is a power. The highest power we can obtain in a certain point. At only certain point we can drain high power. That means we need to maintain this point. This point for particular irradiance, we need to maintain this point to generate maximum power. That means for a particular radiance, then we need to maintain what should be the voltage. The voltage need to be maintained like that. Then this is a power curve. This power curve solar panel is we need to consider when we operate that like that. If we think in the photovoltaic array, shall we think this is a voltage, the voltage output, the photovoltaic output voltage. Photovoltaic output voltage, shall we think of a solar panel? The solar panel is directly coupled to the battery. Yes, there's a solar panel is there. It is directly coupled to the battery. Shall we think the battery voltage is 12 volts? Now the panel is operated at 12 volts. Panel is operated at 12 volts. Any particular radiance, this is the point. Now this operating point is there. Now that is the operating point. Now, actually power is voltage into voltage multiplied by current. Voltage multiplied by current is the current is here. Actually the power we can derive from that area of this curve. That is the area of this curve. Now, actually this operating point in this point, you can see here, this amount of energy is wasted. This amount of energy is wasted. Now, the operating voltage of this solar PV is very much important for a particular irradiance. That means level of irradiance, that point is very much important. That's the point we are calling that the maximum power point is there. Right? Any solar PV, we are calling that the maximum power point is there. That means maximum power point is there. That is we are calling the maximum. There's a maximum power point is there. So what happened? This irradiance is varied. That the level of irradiance, that means level of solar energy is varied. This curves is not same. This per constant, some particular solar radiations, only this curve. This curve also varied like that. This curve also varied like that. That means decrease in solar radiance, this curve also varied. Now, the operating point should be also varied. This operating point should be also varied. These operating points are there. This operating point also should be varied. This point also varied. There's a maximum point also varied. Maximum point of now whatever. If the solar panel is fixed someplace, we cannot say it receives constant solar irradiance. That solar radiations is varied due to time of the day as well as other atmospheric conditions like cloud cover and other things. Time of the day, year of the day, then there are many variations are there. Now there are concepts here. Maximum power point trackers. There's a very important. The maximum power point trackers are the very important. Otherwise, you cannot harness the all energy, the maximum amount of energy which can be generated by that photovoltaic. Then maybe you already know about that solar chargers. Solar chargers. There are two types of solar chargers are there. Pulse width modulation type as well as maximum power point tracking charges are there. Then now we can discuss these things. What are these two types of charges? Because of if you're going to choose, actually for the pulse width modulations mean is not tracking that maximum power point tracking, but it just only pull down that voltage up to battery voltage. Actually, that can be the battery need to be controlled that power because of battery charging. The battery charging need to be controlled. Then if that solar panel is connected to the battery, that the pulse width modulation type charges are used in there. Pulse width modulation mean it generate pulses, the number of the switch off and on time, like that. Off and on time can be changed. That means amount of power drain can be controlled by off time, like that. These type of pulses are there. These type of pulses are generated. We are holding this on time. This is off time. That is off time. Its off time is large, the power drain is low. So on time is high, the power drain is high. Then you can control the amount of power drained by solar panel by using power pulse width modulation type charge controllers. The maximum power point tracking controllers are different. That is different concept. It's track that point. It can be tracked that point, then the output voltage of the panel can be adjusted with respect to that irradiation level by using some maximum power point tracking technologies. There are many technologies are there. Then I'm not going to discuss these technologies in details. Then maybe a quick line method like that type of technologies are there. This is the very efficient concept. This concept need to be used for grid tie type technologies. If the solar panels need to be connected with the grid tie, that means connected to the grid, need to be used maximum power point tracking. Then if it is connected to the battery for a small system, actually these are pulse width modulation type is used for a small system, maybe household system. Even though the battery charging also the maximum power point tracking controllers are there. However, for the small systems, maybe the cost is effective. That's the reason pulse width modulator type charge controllers are using there. Yes. Other thing is that how we can calculate that the peak power calculations. In calculation of peak power, yes, the solar. So solar panel have some amount of energy. Then it's in the nameplate, it's noted that the peak power. The peak power. The peak power definition at 1,000 watt square meter per square meter. If the panel receives 1,000 square meter, 1,000 watt per square meter, at a standard 1.5 air mass spectrum, that means that there's some spectrum distribution is there. When we are calling there's a 1.5 air mass, I can explain that. At the temperature of 25, it generates, there's a peak power. We are calling, actually we are calling the peak power generation. It should be the 90 degrees perpendicular to the solar radiations. Very much perpendicular to solar radiations, and the standard spectrum is there, and solar intensity is defined like that. Then each and every solar panels, if you notice that in the back way in the nameplate, it named as a peak power. What peak power? Like that. What peak power? What peak? What peak like that? That type of notation is there. Maybe 100 watt peak. Just depend on the panel size. However, the peak mean the peak definition is like that. You have to check that. What's the peak power of those are the standard conditions. Now, if we have any solar radiations in particular locations, then shall we think the global horizontal radiations, kilowatt hour per day? Shall we think some locations have different points? Different values are there in Sri Lanka also. If we note some places, the 5, like some places, the 4 kilowatt hours, 4 kilowatt hours per square meter, like this type of place, these locations 4 kilowatt hour per square meter. And then these locations also there. Same thing here. Yes, there is more than 5.2. Here that depends on location. Then daily peak also another parameter. Daily peak we are calling. Then actually daily peak is we can calculate like daily peak. Daily peak is that 1 kilowatt. So average 1 kilowatt. The how much of the time period for receiving 1 kilowatt per square meter, we are calling the peak hours. Then it's the average amount of the 1 kilowatt. Then how many hours we require to receive that amount of energy, we are calling the peak. Actually, we can say the six peak sun hours, 10 to 2 p.m. Then those are the average value. Actually, peak hours are very much important, the place to place, because of that depend on how much of energy received by each and every day. Then actually, this is the values is already indicated with peak hours. And if you need to calculate it like that, shall we think these calculations is very much critical. Let's say we have 2.2 kilowatt peak photovoltaic array. 2.2 photovoltaic array. 2.2 photovoltaic array. We have 2.2 photovoltaic array. Let's say our radiation received in this amount of 4 kilowatt hour per square meter per day. Actually, we can find out with this type of map daily total. This is daily total. Right. Something like here, no? Something like here. This point, like this type of places. This type of places. These type of places. Let's say our location receives that one. how much of energy can generated by this array. Then we can calculate like this type of simple calculation. There are many other assumptions we need to follow that. That means the standard condition 25 degrees Celsius of that panel operations. And if we assume that these conditions are already fulfilled, we can find out how much of energy calculated by that panel. The panel calculation can be approximated like with this type. If you have any panel that like that, shall we think in similar way? That is in Colombo. Colombo, you need to generate like 10 kilowatt hour per day, like that 10 kilowatt hour per day in Colombo. 10 kilowatt hour per day in Colombo. Then what should be your panel capacity? What should be your panel capacity? Like in the Colombo, it is around this range, like that range. It's around 5 kilowatt hour, 5 kilowatt hour per square meter. That is in Colombo. 5 kilowatt hour per square meter. Then if we require 10 kilowatt hour per day, what should be the panel capacity? You can approximate it by this equation. This equation can be used there. Then here that is 10 kilowatt hours. Then the panel capacity need to be calculated. This panel capacity need to be calculated. There's an insolation site is Colombo is around 5 kilowatt hour per square meter per day. Then that's a rough calculation you can follow to estimate how much of the solar panel you may require to generate that required amount of kilowatt hour per day. For a detailed calculation, you need to follow real-time data. The real-time data also can be simulated with the solar panel. The solar panel simulators are there. However, in this level, you should be able to estimate solar panel capacity for a required amount of power generation for if we know the source data. The source data mean site data. The site data is given by the map. If you have the map data, then your required power level also estimated by your requirement. That's in any demand, you can find out. Now, so actually this is the 1,000. Because of this 1,000 is defined. Why we divide by this 1,000? This is 2.2 kilowatt peak. Peak is divided, the 2.2 kilowatt peak is defined at 1,000 watt per square meter. That's the reason it's divided by 1,000. Then it's divided by 1,000. That means divided by 1,000 and multiplied by available resource. Then let's find out the real output of the data, because there's a definition. That is coming from the definition. 2.2 is defined with respect to 1,000. That's the point here. This 2.5, it's a 2.2 kilowatt peak is defined with respect to the 1,000 watt peak. That's the point here. Just the air mass is defined like that because of the spectrum. Generally, there's a spectrum is defined with respect to the how much of distance is traveled through the air. Then this air mass is 1.5. Mean this angle is around the 30 degrees something. Then there's the air, how much of the radiations travel through that atmosphere, that spectrum is changed. You can see here the 1.5 global is this blue. The 1. That's a direct as well as 0 is given there. 0 mean that straight one. It's the lowest distance from the atmosphere. Then actually, this definition is standard. That is standard spectrum for solar panel is 1.5. Now, shall we shall we talk about some applications? Now we have got solar energy in Sri Lanka or in the world. What are the restrictions? What are the main technical barriers to harness that solar energy? What are the, I think some students can be give some answers. Why actually we have large amount of solar. In the world also we have very large amount of solar. You can see here the potential. Yeah, in Sri Lankan situation, what's the potential? You can see a huge amount of potential in the surface area. The large amount of energy there. So why we cannot use that? What's the reason we cannot use that solar energy?
System not allowed for variable voltage.
System not allowed variable voltage.
Sorry, not the voltage, power demand.
Power demand. Yes. Yes, that's correct. What else more?
It can be used only the daytime.
Yes.
Infrastructure.
What do you mean by infrastructure? It's transmission.
Substations and everything.
Yeah, that's transmission. Yes.
Mm.
Some barriers are there. No? How we can overcome those things? Not in Sri Lanka situation. Can you think about the global situation? What are the solutions of these type of barriers? What are the solutions of these barriers? If people are using that renewable energy, not only solar, what are the solutions? Because some countries already have some target also in the maybe 2030. We are going to harness maybe that percentage of the solar energy or some renewable energy. What are the concept? What are the technologies? How we can overcome these things?
Energy storage
Storage
system.
mechanism.
For storage energy. Yes, there is a good. Yes, there's one of the main one, storage energy. The storage energy. Shall we think about it? When we go for a storage for solar, again, the cost of energy also one of the barrier, no? One of the barriers need to be overcome because of storage. Again, that's the cost is coming there. There are some of the concept people are using now to overcome those things.
Generating hydrogen or
Yes.
water pumped to the higher elevations during the daytime.
Yeah. There are options are there, no? Actually, in the solar is only daytime, maybe 6 hours, maybe maximum 8 hours per day, the peak sometime. Especially in a country like Sri Lanka, we have a huge amount of energy at that time. We cannot use that. And what do you think about that? How we can use that solar energy for transportation? So some concept, can you suggest some good concept how we can use solar energy for transportation? because of in the Sri Lankan situation, yes, we have now the large amount of energy we require for transportation. The fossil fuel, how we can use for solar for transportation.
EV cars.
Yes, EV cars is there. Yes, that's a very good concept. If we use that, how we can use the transportation. Now, the charging time can be controlled, no? Like that. The charging time can be controlled. Maybe daytime, we can give some special tariff for charging. No, the very low tariff for the solar peak. Solar peak, we can define somewhat low tariff for to promote people to battery car charging. Like that type of policies we can develop to some level. Yes, some countries, because of now you may know about that the energy curtailment. In maybe Sri Lanka, we are not using the smart grid. Some countries they are using smart grid. The solar PV and wind can be curtailment. There's some curtailment are there. That means the grid had facility to control that energy generation by solar and wind, because of if the grid is cannot be absorb that amount of energy, that the smart grid can be curtailed that power stations like that. That's been the reason in the Sri Lankan situation we cannot use that type of solar generation. Because if we have that type of facility, we can shut down unnecessary that means unnecessary solar generation each and every time, rather than not connected to the grid, because of sometimes we can harness that amount. Then as a curtailment can be used. Then actually I noticed that the country like Scotland, then they have the biggest curtailment of wind power. Then because of they are not much going for a solar energy, because of the solar energy maybe potential may be much not high at these type of countries. The curtailment power is the much more higher than the total requirement of Sri Lanka sometimes. Because of that, even though that curtailment, they harness high amount of energy because of the curtailment is there. Like that in the Sri Lanka also we can use the curtailment, even though curtailment we can harness that. The curtailment can be minimized by using that type of transportation, say battery vehicles that can be promoted to charge that the peak solar time. Then otherwise the one concept is they are the battery. That means that the battery is not an inbuilt battery for transport vehicles. There's a portable battery. The portable battery can be, one battery can be charged at the peak solar time, and it can be replaced because of the daytime need to be run that vehicle. No? Then can be charged and running can be both cannot be do. Then that type of concept can be introduced. The charging there's both way, because of we use that transport for energy storage. That's double benefit, because of energy storage also we are using battery vehicles. Simultaneously the energy balance also there. Then that excess energy can be used for transportation. Then that type of concept we can use to harness that solar energy. Otherwise, we cannot use that the amount of solar. Other important thing to think about the cost of energy. Do we have any idea about the cost of energy of solar? Is it worth to use solar energy? Like when we consider the cost of energy wise, did you notice that in the coal and solar? Shall we compare the coal and solar? Coal is much little bit cheaper now the present situation with the solar. What do you think about that? Is it worth to use solar, even though that coal is cheap? You can discuss.
Yes, because coal produce some harmful gas like
carbon dioxide, carbon monoxide. That's it.
Yeah, there's an environmental effect. No? Can remember that the very first slide I found actually today. I found that some data from calculations. Yes, you can see here. The coal is here, that is 61. Solar is 110. That is utility scale. Residential scale 150. Like in residential scale, now the tariff is not equal to the generation of coal. This is coal sometimes. No? Then some cases that's a situation in Sri Lanka. Even though the residential scale, sometimes solar may be much benefit because of our tariff range may be much more high because there is not a coal tariff sometimes because of some other tariff also. There are other overhead and everything. Then for a detail wise, again case by case we need to find out. But for a national scale, for a utility scale, the energy policy should be there because of the coal also come from foreign currency. I don't know. The solar is also foreign currency. Is it same? Solar also foreign currency.
But only the installation cost dealing with, but running cost, I think all this
Zero.
need more currency.
Yes, but the cost of energy calculation, maybe they already calculated all that cost, capital cost, I think so. No? So for running cost, maybe almost zero there. No? Is it correct? That 110, actually 110 mean is net present value from the capital cost of the contribution. But in the coal, maybe maintenance cost also there, maintenance and operating cost. The PV, maybe I think it is the maintenance and operating cost maybe not much high. Yeah, that's a policy wise we have to think about that the environment because of the environmental effect is not encountered here. Then these things need to be calculated. However, the energy mix should be there in the country. No? We cannot think of only the PVO, only hydro, only coal. However, there are large amount of benefits of each and every sources need to be compared. Do you have any questions to ask for me? Give me another only 5 minutes to give some other concept of few more things to be discussed with you. Some other technologies, new technologies, not new technologies. Just I give some concept of these are there. Solar. The solar chimney also one concept. This is one technological concept. Large amount of power can be generated, but again, need to be think about some other things because of solar chimney. It's a huge cover is there, large amount of solar, the solar the surface is covered by some other material. Due to the cover effect, due to the high temperature of that collectors, it can be huge amount of draft, and that the air can be going through that pipeline. The turbine can be used to generate power. We are calling the solar tower. One more thing I think concentrate solar. Some more things need to be discussed with the Stirling engine. Did you hear about that Stirling engine? Somebody? Stirling engine. The Stirling engine also the external heat source engine. It works with temperature difference, with high temperature to low temperature. Then actually the solar can be used as a high temperature zone and a low temperature zone. This type of Stirling engine can be generate the conversion efficiency is very much high because of the Carnot cycle efficiency. Yeah. Now in the present day, some satellite people are using that. However, the cost of generation is much more high because of the conversion. The technology is high. However, those are some technologies. As a homework, you can find out the concept of the Stirling engine. And you need to, today lessons, you should be able to calculate the amount of power generation by solar panel. This is the very important point need to be learned. Then this remember how to calculate the amount of energy increasing by solar panel. And this is a bit of calculation, very much important to find out capacity of solar. Yes, if you have no any questions, I can wind up the session today. Okay. Oh, please give some.
Okay, sir. Thank you so much.
Okay, thank you.
Mm.
Thank you, sir.
Thank you.